So in the last video, we defined these two different things. One is that we have the derivative of some function f of x at some value, fixed value x equals a. And another one is when you allow that the value of x to vary, we have this notion of the derivative of f of x as a function. And either way, we use this notation f prime of a or f prime of x to denote that. And I just wanted to say a couple different things about this definition before we go through more examples of computing these derivatives. One is that these fractions that you use in the definition of the derivative, these are called the difference quotient. So you're taking the quotient of difference, right? Difference of y value over difference of x value. So these would be referred to as the difference quotient. So another way of saying is that the derivative is the limit of difference quotient. And another thing is when you can find the limit, when the limit exists, we say that the f of x is differentiable at x equals a. Now, if you happen to find the function, again, you can say that the f of x is differentiable as long as this function is defined then, right? F prime of x. Now, I want to give you the same example with the function f of x equals x squared. And now with this, I want to find the f prime of x using the definition. So this is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. And just like we did before, we can find the two different expressions, two terms in the numerator. So f of x plus h is when I plug in x plus h, this x plus h into the function. So I will get x plus h quantity squared minus f of x is just x squared itself all over h. And this is going to be limit as h goes to 0 of, and again, when I expand the binomial squared, please remember that that's not just x squared plus h squared. You will get x squared plus 2xh plus h squared minus x squared. So this minus x squared comes from this one all over h. So now this is going to be limit as h goes to 0. You can definitely see that this x squared and x squared cancel each other out. And what I have left in the numerator is 2xh plus h squared all over h. I guess I didn't have to have that fraction that long. And again, if you were to check the form of this limit, as h goes to 0, numerator definitely goes to 0, and denominator, h is definitely going to 0. So this is definitely going to be 0 over 0 form. But as I said, when you try to compute the derivative, it's always going to give you 0 over 0 form. And so in this case, just like we did before, we are going to factor out the common factor of h in the numerator to get 2x plus h left inside the parentheses. And the common factor of h cancels out. So limit as h goes to 0. And what I have left is just 2x plus h. Okay, so now remember that we're taking this limit as h goes to 0, so I can let this value of h to go to 0. So what I have remaining is this expression 2x. So note that I can write f prime of x is going to be 2x. And notice that the fact that this is a function. So the moment that I want to evaluate this function at different values of x, all I need to do is to plug in the value of that into x, right? So earlier in the previous video, we calculated what this thing is, right? And we found that this to be 4. So this was true from last video. But do notice, once you have that, the f prime of x, if I were to plug that value of 2 into that x, you are also going to get 2 times 2, that's 4. So this is what's really nice about this derivative as a function, right? Because if I wanted to find, for example now, say I want f prime of -3. Okay, so all I need to do is to just take that value -3 and plug that into that x right there. So I am gonna get 2 times -3, and this is -6. So do notice that this is much faster than if I were to go through this definition, -3, which is going to be the limit as h goes to 0. In this case, the value of a is -3, so it's going to be f of -3 plus h minus f of a, which is -3 all over h. So I could do this computation, right, using the definition of the derivative as some value of x, or I can just do that computation and find that the expression f prime of x, as we just did, and use that expression and evaluate this function at different value of x. So this is really nice thing about the derivative as a function. Now I want to also give you different notation for this f prime of x. So the following notation, these are all equivalent. So let's say that this f prime of x. Another way of writing this is use what's called the d notation, df over dx. Now this one is called the Leibniz notation, and this kind of tells you that we are taking the difference of the function value over the difference of x. So this is actually very suggestive. Now if the function happens to be, say if the function happens to be y as a function of x, meaning that the y is the output while the x is the input, then you might also see something like dy over dx. Now you can also see that this comes from changing y over changing x, so this is also very suggestive. Now with this notation, I can also evaluate the function. Let's say if you're going to evaluate this function at x equals a to find the derivative of f at x equals a, you might also see the equivalent notation using df over dx. And in that case, to denote the fact that you're evaluating this function at x equal to a, you're going to see this vertical bar and see x equal to a right next to it, or dy dx. And again, if you see this vertical bar and x equals a, this is indicating that you're evaluating that derivative function at that particular value of x. So I would like you to get used to all of these different ways of writing that derivative. So let's just summarize what we do have. If we happen to find this f prime of x, if you see this notation, immediately what I would like you to be able to say is that by definition, this is limit as h goes to 0 of f of x plus h minus f of x all over h, if this limit exist. So if I were to ask you to use the precise definition of the derivative, this definition is definitely the one that you will be using. So again, if I refer to the precise definition of the derivative, then make sure that you're using this definition. Now, interpretation of that, you can say this is going to be the slope of the tangent line to the graph of f of x at the whatever the value of x it is, right? So this will be the graphical interpretation of what the derivative f of x is. And if you give more general interpretation without referring to any graph, then you can also say this is the instantaneous rate of change of the function value f of x with respect to the change in x. So make sure that you can actually go back and forth between this. So again, precise definition is what's in the red box, but also be able to interpret what the derivative actually gives you in terms of the slope of the tangent line, or just more generally, just the instantaneous rate of change of the function value with respect to the change in the x value. So I want to end this video with the typical example of application. I guess I can say immediate application of the derivative, which comes from this graphical interpretation. So let's just say that you have this problem. Find an equation of the tangent line to the graph of f of x equals x squared at x equals 5. So earlier, we computed this f prime of x as a function, right? So we know that the f prime of x is 2x. Now this would be something that you would actually have to go through the computation for, but suppose that you already went through that and you know this. And knowing the fact that the f prime of x can provide the slope of the tangent line at any value of x, all I need to do is to find the slope of tangent line at x equal to 5. This is going to be given by evaluating the derivative at x equal to 5. Okay, so that means that I need to plug in 5 into this x in this function. So this is going to be 2 times 5. So that's going to be 10. So without going through the derivative computation at x equal to 5, I can just find that derivative function and plug the value of 5 into that to get the slope 10. Well, I just need the point at this point then. So in this case, x value is 5, but the y value at that point is going to be 5 squared. So notice that I'm plugging this 5 into the function itself. So I get that. So what I need is m is going to be 10. And the point that this line goes through is going to be 5, 25 then. So let's just use the point slope formula to get the answer. So just to remind you what the point slope formula looks like, it's right over here. But plug in the slope of 10 and the 0.5, 25, you get this equation. So if I don't simplify anything, this would be your answer then.